Welcome back to another episode of Dave Does Math from Home. This is part 2 of our video about functions and level curves. Part 1 we talked a lot about functions in general, three-dimensional functions, things that you got to look out for. And we talked about a couple kinds of three-dimensional functions. Planes are pretty straightforward in 3 dimensions. Spheres are pretty straightforward. Those are the two that we've actually talked about before in chapter 13. And we also mentioned ellipsoids, or what happens if you take a sphere and you sort of stretch it on one axis or another. On the topic of ellipsoids and spheres, things that are sort of fundamentally round, at least a little bit round, I want to talk about one kind of function we're going to be seeing a lot of throughout the course. Is I call it like a mountain shape. The mountain shape you can get from something like z equals a function of x and y, which is 1 over something plus x squared plus y squared. This is a really interesting shape. I'm going to try my best to draw it. So this, at the end of the last video, I talked about how this x squared plus y squared business is going to come up a lot, and that's how you make shapes that are sort of have rotational symmetry. That, like, what you're interested in isn't really x or y in specific, but x squared plus y squared is like a metric for the distance from the origin. And so if you're using the distance from the origin everywhere instead of specific x and y values, then you can get shapes that, like, at whatever distance, if you pick a distance from the origin, like 3, and then sort of look all the way around at 3, what's happening, it'll be doing the same thing. So this kind of shape here, I'm actually gonna swap this out for now. 1 plus r squared. You remember from polar coordinates that x squared plus y squared equals r squared. This is really what I'm getting at with this distance from the origin bit. In later sections, we're going to switch pretty casually between rectangular and polar coordinates here. So this will be good practice. For now, think of this as a distance from the origin squared. And if you're trying to imagine what this surface looks like, think about it like this. When the distance from the origin is 0, this function is up here at 1. 0, 0, 1. If you go out a little bit, if you want the distance from the origin to be 1, so that's everything that's 1 on the xy plane, everything that has radius of 1, at that distance, this function, or everywhere at that distance, this function is 1 over 2. So you end up with kind of like, at the 1/2 mark from z, 0, 0, 1/2. At this 1/2 mark on z, you end up with sort of like a circle going around this way. And this is radius 1. If you want to stretch the radius out to 2, I'm going to grab a different color for this. When you stretch the radius out to 2, then you end up with a function that looks like 1 over 4. So that's going to be on this axis. That'll be, I'm sorry, 1/5. So now you're down here at 0, 0, 1/5. And that gives you a radius of 2. And then as you increase the radius, this fraction of height decreases continually. So at a radius of 3, this would be 1/10, and it would be much wider and much smaller. So you end up with a shape here that kind of does this, but all the way around. It's like a spike, but it's not like pointy on top. It's like a dome-topped spike thing that sort of flares out on the bottom, and then it comes, it like smoothly curves up, and then it has a rounded top to it. I call it like a mountain shape. This is not an ideal representation of this thing. It's hard to get an ideal representation of this kind of a shape. Trying to draw three-dimensional shapes on a two-dimensional surface is always very frustrating, especially if you, like me, have zero artistic talent for drawing. But there are some tools we can use to help us get a sense of how to draw this better. And for that, I want to talk about level curves. That's what this says. Level curves. I'm going to keep calling this 1 plus r squared. So, what is a level curve? A level curve is, instead of trying to represent a three-dimensional shape on a two-dimensional surface and making the drawing really weird and awkward, we're going to draw the xy plane like normal, and then we're going to pick z values. We're going to fix z at specific values, and we're going to draw those specific curves. When you fix z at a certain value, like right here, if I fix z at 1, that means that the function I have becomes 1 equals 1 over 1 plus x squared plus y squared. This becomes an equation of just x's and y's, and I can solve that. Usually you can end up solving this thing for y. This would become, in this particular case, I would get 1 plus x squared plus y squared equals 1, which means x squared plus y squared equals 0, which means the only solution for this is 0, 0. So this particular level curve, the z equals 1 level curve, is not actually a curve at all. It's a single point at 0, 0. This is z equals 1. But I can pick a different z value, for which I will grab a different color. And I can find the level curve that that value would give me. So for the second one, a second level curve I think should be z equals 1/2. If I fix z equal to 1/2, then this equation becomes 1/2 equals 1 over 1 plus x squared plus y squared, which means that 2 equals 1 plus x squared plus y squared. If I just flip the whole thing upside down, I can subtract 1 from both sides. 1 equals x squared plus y squared. Sometimes you want to solve this completely for y so that you get like a nice shape. Sometimes you can sort of recognize already what shape you're going to get. This is a circle of radius 1. So if the radius is 1, these are all the points where z equals 1/2. We can do, I need to extract some more colored markers from the package. Forgive the weird noises. Okay, here's a real treat. We got purple. We got a brand new purple marker. If we do z equals 1/5, then we have the equation 1/5 equals 1 over 1 plus x squared plus y squared, which means that 5 equals 1 plus x squared plus y squared, which means 4 equals x squared plus y squared. This is a circle of radius 2. So that will be right here. This is the collection of all the points that have a height of 1/5. And you could keep doing this. You can see that this blue point is out here at z equals 1, and the green ring is at z equals 1/2, and the purple ring is at z equals 1/5. And if you sort of imagine these as like altitudes, then you can kind of paint a pretty good picture of what this looks like. It's like making a topographical map of a function. If you are unfamiliar with topographical maps, then you should definitely look them up. They look a lot like this, and they're used in sort of mapping like very hilly or canyonous regions or parks. If you've ever been on like a hike, you might have seen some topographical maps of like when the lines are really close together. I guess I should say, in topographical maps, the different levels are all like a fixed distance apart. So you'll have one line, instead, like I chose the numbers 1 and 1/2 and 1/5 because I knew they'd give me nice little circles. In a proper topographical map, the numbers are they're very uniform. So you'll have like a z equals 10 feet elevation and a z equals 20 feet elevation and a 30 feet elevation and a 40 feet elevation, and the distance between them is always sort of fixed. So if you see an area of the map with a bunch of lines really close together, that means it's really steep there. That's 10 feet of increase on a very small sort of distance on the map. If you see places of the map where lines are really far apart, that means it's very shallow. It takes a long distance on the map for the height to increase or decrease 10 feet. So the idea of level curves is based on the idea of topographical maps, and it's sort of a very accessible way to draw what some of these things might kind of sort of look like sometimes. So this is our mountain, and you can see it's sort of point on the top, and then like as z increases, it expands, and then, as z decreases. You start out with a point here, and then as z decreases towards the surface, that's when it spreads out. There's a couple more functions I want to talk about sort of broadly, and I also want to revisit the idea of level curves with some of the functions we talked about before. So I'm going to go back to our plane so you can see what the level curves of a plane look like, and then I'm going to go back to a sphere so we can see what the level curves of a sphere look like. But something like this will give you the mountain shape. So let's talk about a plane. Let's do z equals, this time let's do 15 minus 3x plus 5y. So if I want to do level curves of this, I need to choose values of z. So z equals 0 is usually a pretty good place to start. Z equals 0 was not a good place to start in the last problem because that function never reached 0. It asymptotically approached the xy plane as x and y became very, very large. It never quite hit 0. Here, this thing will definitely hit 0, so we can start our level curve with z equals 0. That will give us 15 minus 3x plus 5y equals 0, which if we can sort of transform this now into a function of x and y. So 5y equals 3x minus 15, y equals 3/5 x minus 3. So this is pretty easy to draw. There's negative 3, 3/5 x, probably comes out to 5 over here. This straight line is the z equals 0 level curve. And we can make another one. purple marker still in my hand, so we'll do a z equals, let's do a z equals 3 level curve. That will give us 3 equals 15 minus the, minus 3x plus 5y. I don't want to do 3. Let's do 5. 5 equals 15 minus 3x plus 5y, which means that I can subtract 15 from both sides and add 3x to both sides. So I'll have 3x minus 10 equals 5y. And so y should be 3/5 x minus 2. So that would be here. This is the z equals 5 level curve. So on the xy plane, you have this straight line. 5 units above the xy plane, you have the purple straight line that's parallel. I'm going to pick a different color to do another one. Here's blue. Let's do z equals 15. Oh, I erased the function. It's here. I have 15 equals 15 minus 3x plus 5y, which will give me 0 equals negative 3x plus 5y, which means that y should be 3/5 x, no intercept. So that would be this line here. This is the z equals 15 level curve. And at this point you can probably see a pattern. I'm willing to bet that the z equals negative 10 level curve is also a parallel line that goes through negative 5. So, hopefully this is helping to illustrate the linearity of planes in three-dimensional space. They all make their level curves are a set of parallel lines that as z increases, you're sort of moving up, and as z decreases, you're moving down, but they're all parallel and they all have a slope of 3/5. You get parallel lines this way. That's about all the time we have for this video, but there's more still to talk about. We haven't done anything very interesting with domain yet, so we still need to talk about domains, and there's a couple other various level curve-ish problems that we should do. We need to talk about paraboloids. Paraboloids happening in part 3. Stay tuned.